So continuing in with our notes over chapter 12 solutions, we're now looking at partial pressure and mole fraction. I'm pretty sure we did Dalton's law of partial pressures when we talked about gas laws, and it just says that when we have a mixture of gases, this could be a solution where the solvent and solute are both gases, the total pressure is the sum of the individual pressures, and then if we know the total pressure, we can do the mole fraction of the solute times the total pressure to get the partial pressure of that solute. I'm pretty sure we've looked at, so I'm going to move on. Raoult's law says that the total pressure can be greater than predicted. And so this is looking at the force when there's attractive forces between those different molecules. There's a negative deviation that occurs when intermolecular forces between A and B are stronger than those between A molecules and between B molecules. So we have A and B, A is attracted to A, B is attracted to A, but then we have deviations when A and B have stronger attractions towards one another. Because these forces are stronger, fewer molecules escape the solution and the vapor pressure is lower than expected. Remember that when we talk about vapor pressure, for any solution or any liquid, part of those molecules are in an equilibrium where they're constantly getting converted to gas and then back to liquid, and so that's what partial pressure is, or not partial pressure, I'm sorry, vapor pressure. And so vapor pressure gives us the information about those intermolecular forces in those molecules. And so Raoult's law just talks about when A and B have very strong interactions between one another, then the vapor pressure is lower than we would typically expect. Boiling point elevation. When we talk about solutions have a boiling point based on the intermolecular forces involved in that liquid or in that solution. When we look at ions in that solution, we can use the molality and then a boiling point elevation constant known as Kb to look at the change in temperature. So the boiling point gets slightly increased and the freezing point gets slightly decreased when we're looking at solutions versus pure substances. Okay, so this is always a solution versus the pure substance. Boiling point elevation and freezing point depression. So boiling point elevation, delta T, so the change in the boiling point is Kb constant times the molality. So the more ions there are in that solution, or the more concentrated the solute is, the bigger the change in that temperature. Same exact thing for freezing point depression. We have Kf, which is the molal freezing point depression constant. And again, it's just the change in the temperature is K times the molality. So same thing, the more ions or the more concentrated that solution is, the bigger the difference in the freezing point and the boiling point. There are some constants that are common for both freezing point and boiling point that we could use. You can look at the normal boiling point and then that constant if we are calculating at 1 atmosphere. So an example of what this looks like. Ethylene glycol is a common automobile antifreeze. It's water soluble and fairly non-volatile, meaning it doesn't rapidly turn into a gas or it doesn't boil easily. Its boiling point is 197 degrees Celsius. Calculate the freezing point of a solution containing 651 grams in 2,505 grams of water. Would you keep the substance in your car radiator during the summer? And then they give us the molar mass. So we're wanting to look at the freezing point of this solution. So this is that freezing point depression equation. Delta T is Kf times the molality. Remember, molality is moles of solute over kilograms of solvent. And then we plug that into the equation with the K value for ethylene glycol. So we need to calculate molality and then plug in the constant. Molality, again, moles divided by kilograms. So we can just plug in those values, do that normal math that we've done over and over again. So 4.19 molal, and then K from the table was 1.86 degrees Celsius per molal. Multiply 1.86 times 4.19, we get that the change in the temperature is 7.79 degrees Celsius. Pure water freezes at 0 degrees Celsius, and so when we add that change, that negative, I don't know why it says 27, negative 7.79 degrees Celsius instead of 0 degrees Celsius. We can also calculate boiling point elevation in the same way because it was asking us about the summer. So boiling point elevation we'd use the KB value, so we're looking at boiling point, it's 0.52. We multiply 2.2, so normal water boils at 100 degrees Celsius, so then this sample would boil at 102.2 degrees Celsius. And so we would not want that to boil. Another property when we talk about solutions is osmotic pressure, which is a pi symbol, same pi that you use in math. Osmosis is the passage of solvent molecules through a porous membrane from a dilute solution to a more concentrated solution. A semi-permeable membrane allows the passage but blocks the passage of the solute. So a semi-permeable membrane only allows the solvent, so like the water, to pass and not the actual solvent. Osmotic pressure is the pressure required to stop that passage. Okay. Osmotic pressure is calculated as molarity, so we're back to big M, moles per liter. Molarity times R, the gas constant, times T, which is the temperature in Kelvin. We can talk about like the application of solutions and osmotic pressure and things like that when we think about cells in the human body. If you've taken bio, so you've seen like isotonic, hypotonic, and hypertonic solutions. Cells behave differently, and so there's an unequal concentration gradient, meaning that one side is more concentrated than the other. And so when there's this unequal gradient, solvent flows into the cell, and then the cell walls, or the cell swells. It gets bigger because it's absorbing water because of that concentration gradient. The second picture, this one in the middle, that hypotonic, is showing that the inside of the cell is a lower concentration, which causes it to flow out of the cell, and then the cell shrinks in size. So isotonic is equal, hypotonic is low, hypertonic is high. So with hypotonic, it's flowing out. Hypertonic, it's going to flow. I had that wrong. What did we just say? Second photo, hypertonic, second photo, because I'm looking at the wrong one. It's saying the second change photo. So hypertonic is where the concentration flows out of the cell gets smaller, cell gets bigger compared to the initial. Average osmotic pressure of seawater measured in the apparatus shown below is 30 atmospheres at 25 degrees Celsius. Calculate the molar concentration of sucrose, C12H22O11, that is isotonic with seawater. Okay, so when we say sucrose is isotonic with seawater, we are trying to figure out that they have the same osmotic pressure. That's what that's going to mean. And so osmotic pressure is pi equals mRT. We can rearrange. M, our molarity, is pi over RT. We're plugging in the information they gave us, the osmotic pressure, so 30 RT, and then we wind up with 1.23 moles per liter as our answer. That one's really simple, just rearranging that equation. Next example, a 7.85 gram of a compound, empirical formula C5H4 is dissolved in 301 grams of benzene. The freezing point is 1.05 degrees below that of pure benzene. What are the molar mass and molecular formula of the compound? So we know this is my delta TF. This is the freezing point depression. This is the change in the temperature. And so we're going to go from freezing point depression. We know that temperature to find the molality, and then we can find moles, and then we can find molar mass of that compound. So molality is delta T over K. Because we rearranged the freezing point depression equation, we found K from the table given previously because it's a constant, and we can get that it's 0.205 molal. That means 0.205 moles per kilogram of solvent, and the problem told us that there was 301 grams, or 0.301 kilograms of solvent. So we can multiply it and figure out we have 0.0617 moles. Molar mass is grams per mole. We know, given in the problem, 7.85 grams. We just figured out that is 0.0617 moles. So then we figure out that the molar mass of this compound is 127. They gave us the empirical formula, C5H4, which has a molar mass of 64. So this is empirical molecular formula. So the molecular is 127, the empirical is 64. When we divide, that's 2. So instead of C5H4, it is C10H8. So same kind of problem. I'll let you look at this one on your own. But this one, 35 grams of hemoglobin in enough water to make 1 liter. Osmotic pressure is 10 millimeters of mercury at 25 degrees Celsius. Calculate molar mass. So you have osmotic pressure, which then you can find the molality. You can convert that to moles, and then you can find the molar mass. And so it's going to walk you through that. There are some colligative properties of electrolyte solutions. So electrolyte solutions means that we have ions present. Colligative properties depend on the amount of the solute particles in solution, but not necessarily what they are. We just care about the number of solute particles. The Van 't Hoff factor, which is I, is the number of particles in the solution after they separate, divided by the number of formula units initially in the solution. So when we look at NaCl, NaCl separates into 2 ions, and that's in 1 formula unit. CaCl2, we get 3 ions. We get a calcium 2 plus and 2 chloride ions. We get a total of 3 ions in that 1 compound. So really you're just looking at how many ions does it separate out into, is the Van 't Hoff factor, or the I. So we tie these in with boiling point elevation, freezing point, depression, and then osmotic pressure. So same equations, now we just add an I. The more ions or electrolytes that are present, the more it's going to impact it. There's a direct relationship with that. So osmotic pressure is 0.10 or 0.01 molar potassium iodide at 25 degrees Celsius is 0.465 atmospheres. Calculate the Van 't Hoff factor for this. And so osmotic pressure, remember, was MRT. And so we were given that pressure, 0.489 equals MRT. M is the molarity, 0.01, which is given. R is a constant, T is temperature, which is given. And so we're looking, there is 2. We would predict that there are 2 because Ki separates into potassium and iodide. We can solve, it's telling us that it's actually 0.465 atmospheres, so there is a slight deviation from what we would predict and what there really is. We're calculating for I using the pressure that's given. So instead of 2, we're going to put an I there, and we're going to plug in 0.465 because that's what's given. We're going to solve for I. We get that I is 1.9, which is very close to the 2 that we would have predicted just based on the formula. A colloid is a dispersion of particles of one substance throughout a dispersing medium of another substance. When we talk about colloids versus solutions, colloidal particles are much larger than solute particles, and so typically you can see them. A colloidal suspension is not as homogeneous as a solution. You can kind of see the particles floating in there. You've seen colloidal like solutions or particles like in nature and in your life when you see the Tyndall effect, or that light like casting or shadowing, or light scattering, like sometimes in the morning or through different mediums, how that light scatters. That's based on it being a colloidal suspension. It's a hard word for me to say. There's lots of different types of colloids. Things that you are familiar with, things like fog or mist and smoke, whipped cream, mayonnaise, butter, jelly, plastic foams. These are different types of colloids. They're not completely homogeneous, so they're not a solution. The particles are much larger, which makes them a colloid. We can look at hydrophilic and hydrophobic colloids. Hydro meaning water. Hydrophilic is water-loving. Hydrophobic is water-fearing. If you've taken AP Bio, you probably recognize some of these terms, I would assume, because they're bio-related. And so it changes the way that ions behave around whatever it is that we're looking at that colloid. Just an example of something that's hydrophilic versus hydrophobic. When you think about soap and grease, soap is hydrophobic. And so it dissolves into the grease particle because the soap is trying to get away from the water, so it goes into the grease. And then once enough of that soap has penetrated the grease, it's then surrounded by hydrophilic heads, and then that reacts with the water. Okay, that is the end of our properties. I'm going to have you work a colligative properties logic puzzle. It is linked. It's also on Google Classroom if you want to go through the slides. But there are 5 grams of these different substances. They've been dissolved separately in 200 mils of water. They're placed in these random containers, and then they're labeled A through E. So given the data that's down here, you're trying to solve and see if you can figure that out. I'm actually going to post this as an assignment. So once you do it, if you can screenshot or whatever and upload that, this is good practice with trying to figure that out. If you've ever done logic puzzles where you make like the grid, that's how I would approach this, but you can use whatever method works for you. And feel free to work together to try to reason through this because it is kind of complicated.